Okay, here's kind of a cool example. I've got a batter that hits a baseball, and it's 3 feet above the ground when he hits it, and hits it towards the center field fence, which is 10 feet high and 400 feet from home plate. The ball leaves the bat with a speed of 115 feet per second at an angle of 50 degrees. Did this batter just hit a home run? Well, let's start off by making a picture here. So at 3 feet, this person hits the ball and it has this flight path. And eventually it's going to come down. Now, 400 feet away, there's a 10-foot fence. So this is 10 feet. The question is, what's the path of the ball? Does the ball clear the fence? Does it have a path that looks something more like this? Or did it have a path more like the way I first drew it, so it's going to hit the fence? Now, there's a couple of different ways that we could go about this, but my first thought is, if I make this my origin, then really what I need is to figure out whether I cleared 7 feet, because 7 and 3 is 10. So if I can figure out when the ball is going to be 7 feet above the ground, and if it's beyond 400 feet, then that means the 7-foot mark, which is the same as the 10 foot from the ground, is going to be over here someplace. So yeah, it cleared the fence. If the 7-foot mark is somewhere less than 400 feet, then clearly they didn't clear the fence. So this is going to be my first approach. So here's my angle, which is going to be 50 degrees. And this initial velocity vector v naught, the magnitude of v naught, equals 115 feet per second. Let's see, is there anything else here that's of use? No, that's pretty much it. So let's take a look at this. Based on what we did earlier, I know that the position function, r of t, is going to be v naught t, where v naught is the magnitude of the velocity vector at the initial, cosine alpha I plus v naught t sine of alpha minus g over 2, I'm going to write as 1/2 g t squared j. And in this case, because I'm working 400 feet, I'm going to use g as being equal to 32.2. So that's 32.2 feet per second per second. That's the acceleration of gravity. Okay, so with this thought process, this is my x component, this is my y component. So I'm really saying, when is my y component 7 feet above the ground? And once I know what time that happens, I can take that value of t, put it back into the x component and say, where is it? Did it make it over the fence or not? So v naught is 115. So I know that y is equal to 115 t times sine of 50 minus 32.2 over 2. That's 16.1. That takes care of 1/2 g t squared. And of course, I'm going to take this and set all this equal to 7. Well, this is simply quadratic in t. This is now just an algebra problem. And I'm going to write this again, and I'm going to simply write it as, let's see, I'm going to pull this over. I'm going to say 16.1 t squared minus 115 times sine of 50 t plus 7 is equal to 0. See, now I've set up very clearly as quadratic in t, and I'm just going to jump to the old-fashioned quadratic formula. So I'm going to have a negative b, which is negative 115, so that's 115 sine of 50 plus or minus, and quite frankly, I'm not even interested in the minus, so I'm just going to put the plus there. I don't really care what the negative part is. Times the square root of, 115 sine of 50 squared minus 4 times 4a, so that's going to be 16.1, 4ac, that's 7. Over twice a, so that's going to be over 32.2. And that value, when you stick it in a calculator, I'm just going to go out 2 places. That's approximately 5.39. I think when I stuck in a calculator, I got like 5.3911 or something like that. Okay, so what this is saying is that the ball will be 7 feet above, how do I want to say this? Above where it was hit. After it was hit. Okay, so now I can figure out what the x component is. The x component, which is actually I'm going to think of as being distance, how far the thing traveled, is going to be v naught, which is 115, times t, which is 5.39, times cosine of alpha, which is cosine of 50. Oh, by the way, just as a quick reminder, when you do this in your calculator, remember we're working with degrees. If you got some kind of a weird number when you do this, it's probably because your calculator is set for radians. So make sure you go back and forth between radians and degrees, depending on what you're working on. So definitely, the way I'm doing this, I set it to degrees to calculate this with. So when I calculate this out, what I get is 398.43. Now we need 400 plus for a home run. So what this is saying is that there's no home run. Based on our calculations, there's a couple things that we did. This is really close. If I would have gone out 4 places, if I remember correctly, it was 0.3911. This is just a little bit more time. I'm not sure if that's enough more time to get it that extra 1.5 feet that it needs or not. And keep in mind that we're talking about this is with negligible air resistance. In other words, none. It's like a frictionless travel, like through a vacuum, which isn't true. So that would have a counter effect on it because clearly there's air resistance, so it's going to drop a little bit sooner. So this calculation is pretty close, but based on what we're coming up with here, no home run. Nice try. Okay, now there's another approach that we could take to this, which is slightly different, the same idea, but just a little bit different. So what if I said my starting position, let's see, how about this, another approach. What if I said my starting position on the vector r naught, or r of 0, that's 3j. Because remember, I hit the ball from a height of 3 feet, and the ball took off. So r naught is 3j. Therefore, r of t equals negative 1/2 g t squared j plus v naught t plus 3j. Now this, remember, you have to go back a video or two to where we actually derived this thing. And what I did is I simply added to this r naught, or r of 0, which you can think of as r naught. So v naught equals v naught t cosine of 50i plus v naught t sine of 50j. Therefore, r of t, when I combine these things, r of t is going to be equal to v naught t cosine 50i. I could have put this 115 in here for v naught. Plus the quantity v naught t. And actually, I really should, this shouldn't mess you up too much. Rather than doing the 50 and 115, I'm going to stick with alphas for right now, and then we can put them back in. So I'm going to put an alpha right here. So I'm going to have, see, v naught t sine of alpha minus 1/2 gt squared. This is where I stopped before, but now I have that initial position vector, that initial height, which is simply 3. That's that guy right there. All of this j. So now the parametric equations give me x equals v naught t cosine of alpha, and y equals v naught t sine of alpha minus 1/2 gt squared plus 3. So now my approach on this is going to be simply, hey, the ball reaches the fence when it travels 400 feet. So what I'm going to do is I'm going to figure out how long it takes to travel 400 feet. So what I have here is v naught is 115 times cosine of 50 times t, and that needs to equal 400 feet. This is my x coordinate. So that is telling me that the time that's going to take is 400 divided by 115 cosine of 50. So that's roughly 5.41 seconds. So when I put that in for y, what I'm going to end up with is y is going to be equal to 115 times sine of 50 times t, which is 5.41, minus 16.1, that's the negative 1/2 g, times t, 5.41 squared, plus 3. And when I put that in a calculator, what I get is approximately 8.37 feet. So in other words, taking into consideration initial position 3, when the ball has taken off at an angle of 50 degrees, when it traveled 400 feet, the height was now 8.37 feet. So it didn't clear the 10-foot wall. See, the difference in these two approaches is that the first approach, I ignored this 3 feet and just said, okay, I don't need to go 10 feet, I only need to go 7 feet. So I figured out whether that was possible or not. Here I took into consideration the 3 feet, the initial height of the ball, and said, hey, it's got to clear 10 feet. So considering that started at 3 feet, I know after it's traveled 400 feet, it's only 8.37 feet high. It didn't clear the wall, and that's really all there is to it.